Alright, so before I do some more examples of this sort of fancy counting kinds of problems, first I just want to talk about some notation, which you have already seen in the textbook, but I just wanted to make it explicit here. So the number of ways of choosing k things from n options, and here we're assuming that the order does not matter. This is denoted, the textbook uses this NCK notation. N choose k is what that's called. And very often, if you're reading other things online, or if you're looking at my notes that I'm creating here, this notation, n over top of k in parentheses, is very, very, very common. Alright, so this is, I think, by far the most common way that this is written, is this n over k looking notation. Now, just a word of caution, this does not mean n divided by k or anything like that. This is purely notation, right? So this is just a symbol that means this is the number of ways of choosing k things from n options if the order in which they're chosen doesn't matter, okay? So, the way we calculate this, so n choose k is equal to, and remember how we go about this. First, think about the number of ways of choosing the k things from n options if the order did matter. Alright, so I'll make this as a little side note here. So k things from n options if order matters. Right, the way this is done is exactly the same kind of idea that we saw with like our sequential coalitions, for instance. Alright, so we've got n options to go first. Now, we've already chosen one thing, so we have to choose another one that's different from the first. So that would be n minus 1. And we're going to multiply this all the way down until we have n minus k plus 1 things left. Right, the reason why it's going to be n minus k plus 1 is if you think to yourself, let me give you a very specific example here. Right, so if you're trying to choose 3 things from 10, then for the first one you would have 10 options, and then 9 options, and third you would have 8 options. And notice that 8 is 10 minus 3, but that's 7, so add 1 to it. Alright, so that's where this n minus k plus 1 thing comes from. And as you've already seen in the reading, this can be written as n factorial over n minus k factorial. Alright, so the number of ways of choosing k things from n things if the order did matter, well, that would be, sorry, let me do that in the original color. That would be n factorial over n minus k factorial. Right, so this is the number of ways of doing it if order did matter, but we're specifically saying that order doesn't matter. So what you now do is to take this quantity and divide it by the number of ways of reordering the k things that you've already chosen. Right, so the number of ways, I'll use a different color for this. It's the number of ways of reordering the k things you just picked. Well, this is verbatim the same as our sequential coalitions approach. And I've already done this calculation a few times. It turns out to be k factorial ways. Alright, so what we need to do up here, first we've got the number of ways of choosing k things if order matters, and what we need to do next is divide this by k factorial. Right, and this division by k factorial accounts for dividing out the number of ways that those things could be reordered. Right, so this thing is just a formula that you need to have in your back pocket, right? You can either think of it that way, or you can always rederive it the way I just did, right? How many ways are there of doing it when order does matter, and then just divide out all the possible reorderings of those things you just chose. Okay, so this is the general approach. And I just wanted to give you this notation. And again, it could be written as this NCK notation too. It means exactly the same thing. And you read it as N choose K. That's the way you read that notation. And it means the number of ways of choosing K things from N options if the order does not matter. All right, so next let's do some examples. All right, so let's look at a password example. And let's say that we're trying to figure out the number of passwords that have 4 uppercase letters, 3 lowercase letters, and 5 digits. All right, so remember that these problems, these password problems, are always split into sort of 2 big steps that you have to address. One is the issue of formatting, and the other is the issue of figuring out the passwords per format. Right, so you've got to figure out how many total formats there are, and then how many passwords are in each format. Let me address I think the more straightforward of the two is passwords per format. So let me address that here. What I'm going to do here is just pick absolutely any format. All right, it does not matter which format I use here. So I'm just going to pick it the way it's written out right here. Right, so I'm just going to say, all right, I've got uppercase, 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 lower, 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 digit, 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 digit. All right, so that's the format I'm going to use for my representative password here. And now for each one of these things, I'm going to have a number of options that are available to me. All right, so how many uppercase letters do I have? 26, 26, 26, and all the way through to the last 26 here. And for each one of my digits, I've got 10 options. All right, so my fundamental counting principle, or generalized fundamental counting principle, if you like, tells me that I've got this many options that all need to be made. I've got this many decisions that all need to be made. If we count them, 4 upper plus 3 lower is 7, plus 5 digits is 12. So we've got 12 decisions that need to be made to construct this password in this particular format. And we have this many options for each thing, so that's going to be 26 times 26 times 26. How many times? So that's 4 uppercase and 3 lowercase, so that's 7 times. Right, so that's 7 times that I'm doing that. Times. And then we're going to multiply that by 10 times 10, and this is 5 times. Whoops. That's 5 times. All right. So putting this all together, this is 26 to the 7th times 10 to the 5th. And this is passwords per format. Alright, so that's an answer that we are going to keep in our back pocket until we have the other essential part of this, which is the issue of formatting. How many different distinct ways can this password be reformatted? Right, so the U's and the L's and the D's don't have to be all in order like this. They can be jumbled up. And as soon as you interchange one uppercase and one lowercase letter, all of a sudden those two passwords cannot possibly be the same. Right? You've basically completely fundamentally changed the password by moving an uppercase letter and replacing it with a lower, or by interchanging an uppercase letter and a digit, or any two character types, a lower and a digit, right? And no matter what you interchange, you're not ever going to be able to get the same password back by changing that. All right, so we're going to generate this many 26 to the 7th times 10 to the 5th passwords for every distinct format that we can come up with. So how do we figure out this issue of formatting? Well, we need to take a systematic approach. And by systematic, I mean go character by character, meaning character type by character type. So I'll start with the uppercase letters. We have, how many? 4 of these. And we have 4 U's that need to go into, how many total spots did I say? 4, 7 plus 5 is 12. 12 possible spots that the U's can go into. Right, in this format that I drew right here, I just happen to put the 4 U's all at the beginning. Right, spots 1, 2, 3, and 4. But they don't have to be in spots 1, 2, 3, and 4. They could be in spots 2, 6, 7, and 11, right? They don't have to be all in a row. So we've got 4 U's that are going to go into 12 possible positions. And again, I mentioned this in the last video, but I want to make this very clear. If you choose a U here and a U here third, well, that's the same as saying that you've got a U third and a U first. Right? The order in which you say that those two positions are taken by uppercase letters, it doesn't matter which order they're in. You still get the same format. Right, so let's just pretend for a second that I did interchange the U that's first with the U that's third. Well, then the beginning of my password still looks like UUUU, right? Here, if I change the colors a little bit, maybe it'll make it clearer. Right, let's say I'm going to take the green and the dark blue ones and interchange them. All right, so if I do the old switcheroo with those, right, so I've switched the order of these two to get this new, quote-unquote, new format down below. Is that a genuinely new format? Well, the answer is no, because you still just have 4 uppercase letters in a row. Right, as far as the format is concerned, these are identical. All right, so the point that I'm making here is that we have 4 U's for 12 spots, and the order doesn't matter. Right, the order in which we list these U's does not matter. All right, so what that tells us is that the number of ways of doing this will be 12, the number of total spots available, choose 4. We just need to pick any 4 of those spots for our uppercase letters to be in. And the order in which we choose them doesn't matter. All right, so this is going to be 12 factorial over 12 minus 4 factorial times 4 factorial. And here I'm just using this formula that I derived right here, with n equal to 12 and k equal to 4. All right, so this is 12 factorial. 12 minus 4 is 8, so that's 8 factorial times 4 factorial. And now, very often, students are inclined to say, okay, I'm going to take 12 factorial and I'm going to plug it into a calculator. I'm going to compute 8 factorial and, by plugging it into a calculator, and same for 4 factorial, and then I'm going to have hideous, awful, monster number upstairs, hideous, awful, monster number downstairs, and I'm going to make a calculator do that division for me. This is a catastrophic way of doing this problem. Do not do that. the thing that I want you to do here is to recognize that there is an incredible amount of cancellation in every one of these problems. All right, so to see that, let's rewrite 12 factorial. Right, 12 factorial, by definition, is 12 times 11 times 10 times 9 times 8 times 7 times all the way down to 2 and 1. Right, this is the definition of 12 factorial. And now the thing I want you to notice is that what is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1? Right, what is that thing living inside of 12 factorial? Well, this is nothing more than 8 factorial. And look, 8 factorial is in our denominator. So what's being said here is that this 8 factorial that's being divided, that's going to cancel out the 8 factorial that lives inside of 12 factorial. All right, so what we're going to be left with if we make that cancellation, upstairs will be 12 times 11 times 10 times 9. Everything from 8, 7, 6, 5, 4, 3, 2 down to 1 all canceled out because that was just another way of writing 8 factorial. All right, so downstairs we're left with 4 factorial, which is just 4 times 3 times 2 times 1, of course, but I can leave that off because multiplication by 1 is not changing the value at all. And now at this stage, you really just want to cancel whatever you can see, all right? It becomes a free-for-all at this point. So for instance, I see that 4 times 3 is 12, and I've got a 12 upstairs, so I can cancel those. I've got a 2 here, and I only have one even number upstairs, which is 10, which I'll replace by 5. All right, so after all that, I'm left with 11 times 5 times 9. Oh, is there a clever way to do this multiplication? Maybe. So this is 55 times 9. Now, if this were 55 times 10, that would be 550. But it's times 9, not times 10. So subtract 55 from that. And so this is 495. All right, so there are 495 ways of choosing just the positions of the 4 uppercase letters. Right, 495 possible ways of choosing the positions of the uppercases in this password. All right, so for for the second thing we have to do here, we have 3 L's to place, and we started with 12 spots, but we just picked 4 of those spots to be occupied by U's, uppercase letters. So that knocks us down to 8 spots remaining. All right, and the way we're going to do this is exactly the same. This is going to be 8 choose 3. And this is 8 factorial over 8 minus 3 factorial, which is 5 factorial, over 3 factorial. And now I'm going to make the exact same observation I made in the last part, and realize that 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and 5 times 4 times 3 times 2 times 1 is 5 factorial. That means I can cancel them out and just be left with 8 times 7 times 6 upstairs. Downstairs, 3 factorial, which is 3 times 2, which is 6, and so I'm left with 8 times 7, which is 56. Alright, so 495 ways accounted for the U's, 56 accounts for the L's, and we only have one other character type, which is the D's. And if you remember back to the end of the last video, if we take 3 spots of the 8 that remain and we fill them with L's, then we're left with 5 spots for 5 digits. And there's only one way that you can put the 5 digits in the 5 spots that remain, right? It's like if, if you need to seat 5 people and there are 5 chairs, well, you just sit everyone in a chair. And this is important, that the order doesn't matter for this. If the order did matter, it would be more complicated, but it doesn't matter. So there's exactly one way of positioning the digits after you've positioned the other two kinds of characters. So, putting this all together. Alright, so all together now. What we have is the number of passwords will equal number of formats times passwords per format. And we just figured out from the last page that the number of formats are 495 times, what number did we get? 56 for the lower cases. Times one way of arranging the digits when all is said and done. So we have 495 times 56. All right, this is the number of ways of choosing the first decision you have to make in a format, which is deciding where the uppercases go, times the number of ways of deciding where the digits go, where the lowercase letters go, which is your second decision to make in creating this format. And then we're going to multiply that by the number of passwords per format, which is right there, 26 to the 7 times 10 to the 5. Bad notation here, mixing your crosses with your dots, so I'll make them all dots. Alright, this is how many passwords there are. There is no way that I can think of, anyway, to make this into anywhere near a reasonable looking number. This is it, right? This is as good as it's going to get, as far as an exact answer goes. And of course, if you want an approximation, I'll leave that to you guys. This is going to be an absolutely massive number. Right, there are a lot of these passwords. Okay, so the thing I want to do next is to take a good thing and make it even better. But unfortunately in math, making things better usually means making them harder. However, the thing I want to do next is something that I think people can get a handle on, because it has to do with something that almost certainly all of us have done at some point in our lives, and that is play cards. Right? Any kind of cards. I'm going to use a standard 52 card deck of playing cards. So I'll remind you first what the 52 card deck looks like, and then we'll start to answer some basic questions about how many different ways there are of choosing various hands of cards. Alright, so just so we're all on exactly the same page here, a standard 52 card deck contains 4 suits. I've drawn them crudely here. This one is clubs. This one is diamonds. This one is hearts. Oof, that's a train wreck. Let me try that again. Hearts. And the last one is spades. Traditionally, clubs and spades are referred to as the black suits. Diamonds and hearts are referred to as the red suits. And each one of these suits has 13 cards. 2, 3, 4, all the way up through 10, followed by Jack. Right, so writing these out, this one is Jack. This one is Queen. This one is King. And A is for Ace. Alright, and just to double check the math here, the number of suits is 4. Every suit has 13 cards, so checking the total number of cards, 4 times 13 is 52. Alright, so this is a 52 card deck. Now, let's try to ask a question. How many 5-card hands contain exactly one pair? Alright, and here, just in case you're unfamiliar with the language, a pair means 2 cards of the same rank. Meaning, for instance, the two, let me use standardized colors here, the 2 of clubs and the 2 of spades. Alright, that would be a pair of 2s. So, how many 5-card hands contain exactly one pair? Now, this is this kind of way of approaching these problems that I'm about to introduce takes practice. Alright, this takes a lot of practice. So here's how I'm going to view this. We need to build, a 5-card hand. Hand. Alright, so we're going to have 5 cards that we need to populate, right? We need to build this 5-card hand. And what we're going to do is we are going to be systematic about this. I'm going to say that these 2 cards are going to be my pair. And the rest of these 3 cards will just be everything else in my hand. Alright? So, we are going to treat this, again, systematically. I'm going to view building this 5-card hand as 2 decisions that need to be made. I first need to build my pair, and then I need to build everything else that goes into my hand. So, how many ways can I build the pair, just the pair? That's a number of ways of getting a pair. Well, I have 52 cards available to me, right? So I'm trying to choose card 1 and card 2. So I have 52 cards available to me for the first card. Right? Could be any of the 52 cards in the deck. The thing I want you to think about: how many cards do I have for my second card? Alright, in how many ways can the pair be completed? Alright, so think about this before you start the next video. If you want a concrete example, let's say this first card is a king. Right, let's make it specific. Let's say it's a king of hearts. How many other cards are in the deck that will complete this pair? Right, that's the question I want you to answer. If you can answer that, I want you to try and attack this issue of choosing everything else. Right? How can you make sure that you're counting the right thing by specifying that you want to have exactly one pair in your hand? Alright, so there's a little bit of stuff you have to be careful about there. Think about these things. In particular, definitely 100% think about this question down here. Alright, see if you can answer that question, how many options you have for your second card. And then start the next video.